We'll start in about 3 minutes. Okay, we'll go ahead and start. Today we'll look at the Test 2 review sheet. There won't be enough time to work out every problem completely, so I'll at least try to set up some of the ones. For the first one, Simpson's rule, and since we have 6 intervals, the Simpson's approximation S sub 6 is delta x over 3, so delta x is 2, that's the length of each subinterval, so 2/3. And then it's g of 2, which is 11.6, and then plus 4 times 11.6, which is g of 4, plus 2 times 11.1, plus 4 times 11.7, plus 2 times 12.2, plus 4 times 12.6, and then plus 13. So if you have something on a test, this would be an okay answer. The thing that you would be tested over is, do you have the delta x over 3, and then do you have the correct scalar multiples of the function values on the inside? And the trapezoidal rule, I'll leave that one for you to do. That one's even easier to remember than Simpson's rule. Okay, for problem number 2, do the integrals converge or diverge, and evaluate those that converge. On this one, you can change variables if you want. You can assign u to be equal to 2x plus 3. So du is 2 dx, which means 1/2 times du is dx. And then you can convert this Let's see, the lower limit x equals 1, if we convert that to a u value, 2 times 1 plus 3 is 5. If x approaches infinity, then so does u, so the upper limit is still infinity. And then replace dx with 1/2 du. So I'll put the factor 1/2 on the outside, and then 1 over u to the third du. So we can tell by looking that this is going to converge. So let's just take it a couple of steps further. For this kind of improper integral, we'll write it as the limit as b approaches infinity of the definite integral from 5 to b, and then I'll replace 1 over u to the third with u to the negative 3 du. And then compute the integral. Okay, so an antiderivative of u to the negative 3 is u to the negative 2 divided by negative 2, or negative 1 over 2 times u to the second. And then evaluate that from 5 to b. So this is 1/2 times the limit as b approaches infinity. So we have negative 1 over 2 b to the second minus a negative or plus 1 over 2 times 5 to the second, or 1/50th. And then as b approaches infinity, this first term, negative 1 over 2b to the second, approaches 0. So the limit is just 1/2 times 1/50th, or 1/100th for that limit. Okay, the next one, well, if you rewrite the integrand so that we have this improper integral of 1 over x to the 2/3 dx, then we can just say this diverges because the exponent on x in the denominator is less than 1. So this diverges, if you remember that. It wasn't really called a theorem, but in effect it's a theorem. If you have 1 over x to the p, then it diverges if p is less than or equal to 1, and it converges if the exponent is greater than 1. Here on this one, we have another improper integral. Why is this improper?
Negative 3 plus 3 equals 0.
Yeah, negative 3 makes the denominator 0, so this is undefined. So we deal with this one if we take the limit as b approaches negative 3 from above. And then we have this, from b to 6. And then I'll rewrite 1 over the square root of x plus 3 as x plus 3 to the negative 1/2. And then compute the integral. Okay, an antiderivative of x plus 3 to the negative 1/2 is x plus 3 to the 1/2 divided by 1/2, or 2 times x plus 3 to the 1/2. And we evaluate that from b to 6. So a couple more steps. So we have 2 times, and then when x is 6, 6 plus 3 is 9. 9 to the 1/2 is 3. And then minus 2 times b plus 3 to the 1/2. Okay, so when b gets close to -3, b plus 3 gets close to 0. So the limit is 2 times 3, or 6. Okay, the next page. Determine the arc lengths of the curves. Well, there are 3. For now, let's just set up one of those. So if y equals x to the 3/2 on the interval from 0 to 4, we want to know what the derivative is. So we get 3/2 times x to the 1/2. And then we're going to compute 1 plus the square of that derivative. So 1 plus, and then when we square 3/2 x to the 1/2, we get 9/4 x. So we're going to write this as 4 plus 9x, all divided by 4. So that is what, let's see, I guess we're using L for the arc length. So that's the integral from 0 to 4 of the square root of 1 plus the derivative squared. So the square root of 4 plus 9x over 4 dx. So I think this one is simple enough for you to complete. You know how to compute that derivative, or that integral, I mean. Okay, so let's move on to part 4, finding the surface area. Okay, this one, y equals the square root of 5 minus x on the interval from 3 to 5. We're going to rotate that about the x-axis and find the surface area. Okay, so I'll rewrite what y is. I'll write it as 5 minus x to the 1/2. And we want the derivative of that, dy dx. So we get 1/2 times 5 minus x to the -1/2 times -1. Or -1 over 2 times the square root of 5 minus x. Okay, and we're going to square that. So part of this integrand is going to be the square root of 1 plus dy dx squared. So that's going to be 1 plus this thing squared, which is 1 over 4 times 5 minus x. Okay, so the surface area, the integral from 3 to 5 of 2 pi, we're rotating about the x-axis, so it's 2 pi times the square root of 5 minus x times the square root of this. So 1 plus 1 over 4 times 5 minus x. If we write it as a single rational expression with the denominator of 4 times 5 minus x, then the numerator will be 4 times 5 minus x plus 1. So we'll put this inside the square root. So in the denominator, we'll have 4 times 5 minus x. And let's go ahead and simplify the numerator. So the numerator is going to be 21 minus 4x. And then dx. Okay, so we get some simplifying to help us out a little bit. Notice this square root of 5 minus x is going to cancel with the square root of 5 minus x in the denominator. And then the square root of the 4 in the denominator, that comes out as 1/2. And if we multiply 2 pi times 1/2, we just get pi. So let's write it one more step. The integral from 3 to 5 of pi times the square root of 21 minus 4x dx. And I think that you can find the value of that definite integral. Okay, are we all okay on that one? Okay. So let's move on to the next page. Suppose a vertically oriented isosceles trapezoid is in water. The top is 10 feet long, and at the water level, the height is 15 feet, and the bottom is 30 feet long. Find the hydrostatic force on one side of the trapezoid. Okay, so at the water level, we have the top of the trapezoid, which is 10 feet. And my drawing probably won't be to scale, but the base is 30 feet. So by isosceles, it is meant that this slanted side has the same distance or the same length as this one, and those two sides are parallel. And the height of the trapezoid is given to be 15 feet. So one thing to note is if we look at this right triangle, then each of those three parts is 10 feet. And if we define the positive x-axis to be vertical and moving in the downward direction, then our depth will be represented by x sub I. So we want to come up with an expression for the area of a rectangle that spans the trapezoid at each depth x sub I. Okay, so we'll use similar triangles to help us out. Let's refer to this distance here as W. So that means this is also W and this is 10. So the length of this rectangle is 2W plus 10. And we need to be able to express W in terms of X. Okay, so let's look at that right triangle in isolation. So we have 10, this side is 15. And then from the surface moving downward, we're going x sub I units, and this is W. So using similar triangles, W divided by x sub I is equal to 10 divided by 15, which we will simplify to 2/3. And so W is equal to 2/3 times x sub I. Okay, so the length of this rectangle then is 10 plus 2 times 2/3 x sub I. The width of that rectangle is delta x. So the area of that rectangle is length times width. So we can write it as 10 plus 2 times W, which is 4/3 times x sub I, and then times delta x. And then the d sub I is just what x sub I is. So remember our formula for the hydrostatic force on that rectangle, the ith rectangle. It's rho times g times the area of the rectangle times the depth, d sub I. So in particular, rho times g is 62.5. This is the area. I don't have room to write it up here, but then the depth is x sub I. So if we do that for each of the sub-rectangles on the trapezoid and add them up and then take the limit, then the hydrostatic force, the limits of the integral will be from 0 to 15. And then 62.5. And then the area times x. So I'm going to multiply x times the quantity 10 plus 4/3 x. So we get 10x plus 4/3 x squared, and then dx. So you can evaluate that integral. For now, let's bypass number 6. If we have time, we can come back to that one. Okay, number 7, find the centroid of the region bounded by y equals x to the third, y equals 0, and x equals 2. So remember, y equals 0 is the x-axis. So I'll just do a rough sketch of y equals x to the third. So this is not completely accurate, but we'll get an idea. So we want to find the centroid of this region. So to find the moment of the region about the y-axis, that's going to be, well, we have this rho constant. Rho times the definite integral from 0 to 2 of x times f of x. So our f of x is x to the third, so x times x to the third is x to the fourth dx. Okay, so this one's pretty simple to find. Rho times x to the fifth divided by 5 from 0 to 2, or 32 fifths times rho. And then the moment of the region about the x-axis, is rho times the definite integral from 0 to 2 of 1/2 the square of f of x. So since f of x is x to the third, when we square that, we get x to the sixth. So this is also pretty simple. So we get rho times 1/14 x to the 7th from 0 to 2. So 2 to the 7th is 128 divided by 14 is 64 over 7. So I get 64 over 7 rho for the moment about the x-axis. Okay, then the mass, that's rho times the area. So rho, and then the area is just the integral of the function f of x from 0 to 2. So this is rho times x to the 4th over 4 from 0 to 2. And we get 4 times rho. And then the x-coordinate of the centroid, x bar, that's the moment of the region about the y-axis divided by the mass. Okay, so when we divide 32/5 rho by 4 rho, the rho's cancel, and we're just going to get 32 over 5 times 1/4 or 8/5. And then the y-coordinate of the centroid is the moment about the x-axis divided by the mass. So 64 over 7 rho divided by 4 rho, the rho's cancel, and we're just going to get 16/7 when we simplify it. So we'll check to see if it is at least in the region, 8/5, and then 16/7. Well, my graph is not really to scale, but it's right in there somewhere. So it looks like we're at least in the region. Okay, let's, for now, we'll bypass the centroid of this other region. And let's look at problem number 9. Okay, a 1,000-gallon tank is filled with gasoline containing 15 pounds of an additive. A gasoline mixture containing 0.02 of a pound of additive per gallon is added to the tank at the rate of 50 gallons per minute. Assume the gasoline solution is continuously and thoroughly mixed and drained out at the same rate of 50 gallons per minute. Find a function that measures the number of pounds of additive in the tank after t minutes. Okay, so we define some function, say a of t, to be the number of pounds of additive in the tank. We're measuring in minutes after t minutes. So this is number of pounds of the additive in the tank at t minutes. Okay, so we're going to write down a differential equation. The rate that the additive in the tank changes with respect to time in T minutes. We're told that a gasoline mixture containing 0.02 of a pound of additive per gallon is added to the tank at 50 gallons per minute. So if we have 0.02 pounds per gallon multiplied by 50 gallons per minute, then the gallons units cancel, so this is going to simplify to 1 pound of additive per minute is being added to the tank. 0.02 times 50 is just 1. But then out of the tank is being drained a thoroughly mixed solution. So what do we subtract? Well, it's whatever the amount of additive is divided by the total number of gallons, 1,000, times the rate at which it's being drained, which is also 50 gallons per minute. Okay, so when we write the equation without the units and simplify the arithmetic, we get 1 minus 1/20th times A. Okay, but let's write this as 20 minus A over 20. And what we have is a separable differential equation. So when we separate the variables, we get the differential dA divided by 20 minus A. Equals 1/20th dt. Okay, so yesterday there was a question about what took place when we found the antiderivative of this. So if we just look at that in isolation, you have 1/20 minus A dA. And then if you assign u to be 20 minus A, du is negative dA. And so that means negative du is dA. So when you make substitutions, this will transform into negative integral of 1/u du. You probably already figured that out. But.
That's actually very helpful.
Okay.
Just think about it that way.
Mm-hmm. Okay, so when we compute the antiderivative of this, well, the antiderivative of this is negative natural log of u, but since u is 20 minus A, here we'll write negative natural log of 20 minus A. And then an antiderivative of 1/20 with respect to t is 1/20th t, and then plus a constant. So I'm sort of out of space. Does everyone know what to do from here, or do you want me to keep going? We've seen it a few times. I'll take it a little bit further. Multiply both sides by -1, so we get the natural log of 20 minus A equals negative 1/20th t minus c. Then if the natural log of something equals something, then 20 minus a equals e to that, which I'll write as e to the negative c times e to the negative 1/20th t. So solve for a, then use the initial value. The initial number of pounds in the tank is 15. So the initial value is a of 0 equals 15. So there's a little bit more work there to do, but I think you can probably get that. Okay, let's move on to the differential equations. So there's a question on YouTube. Aren't you supposed to subtract f of x minus g of x? So which problem are you referring to? Problem number 7. Well, I think if that's what you're referring to, since the lower bound is y equals 0, then we didn't need to subtract, because x to the third minus 0 is just x to the third. On the other problem that we didn't do, so on this one, since the lower function isn't y equals 0, then you do have to subtract when you're finding the centroid of this one. Okay. And number 10, solve the following differential equations. So there are two kinds of differential equations that we've discussed. One is a separable differential equation, and the other one is a first order linear. So those are the only two that you're going to have to know how to do for the test. So what kind is this one? Y prime equals x times e to the negative 2y. It's separable. Is that what you said?
No.
Oh. Yeah. Why isn't it linear?
Because there's no t of x, y term on the other side?
Or there's not a y by itself. There's a e to the negative 2y, but that's not a linear, that's an exponential. Okay, so rewriting y prime as dy dx can help. And then if we multiply both sides by e to the 2y, we'll get e to the 2y dy dx equals x. E to the 2y times e to the negative 2y is just 1, right? If you want to think about dividing both sides by e to the negative 2y, you can. But if you have 1 over e to the negative 2y, that's equivalent to e to the 2y in the numerator. And then we write this as e to the 2y dy equals x dx. And then we integrate both sides. So I'll skip the step where I write the integrals. So when we integrate, we're going to get 1/2 e to the 2y equals 1/2 x to the second plus a constant. And then to determine what the constant is, we use the initial condition. So this means when x is 0, y is 0. So we replace x with 0 and y with 0. So 1/2 times e to the 2 times 0 is e to the 0 equals 1/2 0 to the second plus c. Or 1/2, e to the 0 is 1, so we get 1/2 equals c. Okay, so let's write that 1/2 e to the 2y equals 1/2 x squared plus 1/2. Sometimes you'll see answers like this where they don't actually solve for y. But we can solve for y. We can multiply every term on both sides by 2 just to get rid of the fractions. So if we multiply every term on both sides by 2, we get e to the 2y equals x squared plus 1. And now how do I solve for y? Yeah, take the natural log of both sides. The natural log of e to the 2y is 2y. Natural log of x squared plus 1. And so y is equal to the natural log of x squared plus 1 divided by 2, or 1/2 times the natural log of x squared plus 2, or you could write that as the natural log of the square root of x squared plus 1, if you want. Those are all equivalent, right? Okay, the next one, y prime equals the natural log of x divided by y squared. Y of 1 equals 6. So I see a y squared, so it's not linear. So it is separable. Write y prime as dy dx. And then we can separate the variables. So on the left-hand side, y squared dy. On the right-hand side, the natural log of x dx. And then integrate both sides. An antiderivative of y squared with respect to y is y to the third over 3. And an antiderivative of the natural log of x. X times the natural log of x minus x plus a constant. I'm going from memory, so you might want to check me out on that one. So at this stage, we can determine what c is, even though we don't have y solved for yet, but that should be okay. Oh yeah, okay, y of 1 is 6. So let's see, 6 to the third, replace x with 1 and y with 6. So 6 to the third is 216 divided by 3 equals 1 times the natural log of 1 minus 1 plus c. The natural log of 1 is 0. 216 divided by 3 is 72. 72 minus 1 equals c. 72 plus 1 is c. Okay, so let's go back to this stage with the c. So y to the third over 3 equals x times the natural log of x minus x plus 73. So just a couple more steps. I would consider this an okay answer, but you can multiply both sides by 3 and then take the cubed root of both sides if you want. So let's get on to another kind. So we haven't seen a first order linear yet. So let's bypass this one for now and try to find a first order linear differential equation. So this looks like one. This has the form y prime plus p of x, y equals q of x. First order linear. So p of x is negative x, and so our integrating factor is e to the integral of negative x dx. So that's e to the negative x squared over 2. Okay, so we multiply every term on both sides of this by the integrating factor. So we get e to the negative x squared over 2 times y prime, and then minus x times e to the negative x squared over 2y, and that's equal to x times e to the negative x squared over 2. So the left-hand side is the derivative of e to the negative x squared over 2 times y. So we can always verify. So yeah, it looks like we're okay. So when we integrate the derivative of a function, we just get the function on the left-hand side. So the left-hand side after integrating is e to the negative x squared over 2 times y. And what about the integral of the right-hand side? So if we look at that in isolation, x times e to the negative x squared over 2 dx. How should we go about integrating that? If you let u be the exponent, negative x squared over 2, then du is negative 2x over 2, or negative x dx. So we have the x dx, we just need the negative, so negative du is equal to x dx. So upon substituting, we just get the negative of the integral of e to the u du. And so that's going to be negative e to the u. But u is negative x squared over 2. So this is going to be equal to, after we integrate, negative e to the negative x squared over 2 plus a constant. Okay, the next thing to do is divide both sides by e to the negative x squared over 2 to solve for y. But while we're at this stage, why don't we go ahead and find c? When x is 0, y is 2. So when x is 0, this becomes e to the 0 or 1. And we replace y with 2. And this is negative 1 plus c. So c is equal to 3, it looks like. Okay, so I'll see if I can squeeze all of that in. We're going to divide every term on both sides by e to the negative x squared over 2. So the left-hand side will be y. And when I divide this by that, I just get negative 1. And if I divide 3 by e to the negative x squared over 2, that's equivalent to 3 times e to the positive x squared over 2, isn't it? So that's what I get. Okay, we have less than a minute. This next one, I'll just do the first step. This is a first order linear. So the first thing to do is divide every term on both sides by 2x. So you get y prime plus 1 over 2xy. And then 10 times the square root of x divided by 2x becomes 5 over the square root of x. And we're out of time now. But so we saw a pretty good sample of problems on the test 2 review sheet. If you get stuck on any of the other ones that we didn't cover, you can send me an email. And maybe I'll just write out the solutions and email them at some point. Okay, that's all for today.
Having a midterm, or is this our midterm? Are we going to have a midterm, or is this our midterm?
Yeah, this one is yeah. I just have 4 regular tests and then final after that.
All right. We're going to need to get my syllabus.